Hey guys, Mr. Backerberg here. In this video, we're going to look at absolute, relative, and percent change. So as we move from A to a nearby point A plus delta x, we can describe the change in f in three ways. Now the first one is the absolute change. Now there's going to be true ways to calculate these and then our estimated ways to calculate these. So to find the true absolute change, so this delta f, what we would do is take f of a plus dx, or the change in x, minus f of a. And then our estimated way, what we did is take the derivative of f at a and then multiply by dx, or the change in x. The next thing we've got is the relative change. So the relative change takes the absolute change and divides it by f of that starting a value. And the same thing holds true for the estimated relative change as well. It takes that estimated absolute change and divides by f of a. And then our last one is the percent change. So the percent change takes the relative change and we turn it into a percent by multiplying by 100. Same thing for the estimated version. We take the estimated relative change and multiply that by 100. So in this example, we're going to look at changing the radius of a bicycle tire and see how it affects those different types of changes. So we'll look at the absolute change, the relative change, and the percentage change, all for this one example. So the first thing we're going to look at is the absolute change. So what we're going to do is inflate a bicycle tire so that its radius changes from 12 inches to 13 inches. And we're estimating that absolute change in the perimeter of the tire. Now, because our tire is circular, then the perimeter of the tire is really going to be the circumference. So we can talk about the perimeter as being 2 times the radius times pi. So we're going to estimate the absolute change in the perimeter. So the change in the perimeter is going to be the derivative of the perimeter function at the starting radius of a, but then we're going to multiply by the change in the radius. So if we look at finding the derivative of that perimeter function, that r is really our variable in here. The 2 and the pi are constants. So if we differentiate that, then we're just going to end up with 2 pi, but then we also want to multiply by the change in the radius. We started at 12 inches and we moved up to 13 inches. So the change in the radius is going to be 1 inch. Now, technically, we're supposed to do the derivative of p at a, but because there is no r value left in here, we don't have a place to plug in the 12, so we're not going to plug that in. So we end up getting 2 pi as the absolute change in our perimeter, and we can approximate that to be about 6.28 inches. Now, in this part, we're going to approximate the relative change in the perimeter of the tire. And to do the relative change, we said that we were going to take the absolute change and divide by the function at our specific a value that we started with. So we just found an absolute change of 2 pi inches. Now we're going to divide that by the perimeter at that starting a value. And again, we know that the perimeter is 2 times the radius times pi. So if we plug in our starting radius of 12 inches, 2 times 12 would be 24. So this would be 24 pi. If we divide this out, the pi on top and on bottom cancel each other out. And then we can reduce down the 2 and the 24, so we get about 1/12, which if we approximate that out to 2 decimals, it's about 0.08. And then the last thing is that percent change. So for the percent change, we take the relative change that we just found and multiply it by 100. Well, we just found a relative change of about 0.08, so if we multiply that by 100, then we can say that's about an 8% change. Now in this example, we're going to look at estimating the Earth's surface area. So suppose the Earth were a perfect sphere, and we determined that its radius was about 3,959 miles, plus or minus 0.1 miles. And we want to figure out what effect that tolerance of plus or minus 0.1 miles would have on our estimate of the Earth's surface area. Well, first thing we should talk about is the surface area formula for a sphere, and that's S equals 4 pi r squared. So we want to figure out specifically what effect that tolerance would have on this surface area. So we want to find the change in the surface area. So what we're going to have to do is take the derivative of the surface area formula and then multiply by the change in the radius. So that tolerance is going to be our change in the radius. As far as the derivative of the surface area formula, r is our variable, so if we use the power rule there, drop the 2 down as a multiplier, and this is going to be 8 pi r, but then like we said, that 0.1 is going to be our change in the radius. Now as we're calculating the change in the surface area for that r value, we want to plug in the 3,959. So this is going to be 8 times pi times 3,959 times the 0.1. Now, if we were to multiply all of that out, we're going to get an approximate change of about 9,950 square miles because we're talking about area. And that sounds like a lot. It's actually an area about the size of the state of Maryland. But if you're looking at the surface area of the whole Earth, then that really isn't that much at all. So that 0.1 change in the radius is really going to have very little effect on the overall surface area of the Earth. Now in this example, we want to look at determining some tolerances. So we want to figure out about how accurately should we measure the radius of a sphere to calculate the surface area to be within 1% of its true measure. So we want any inaccuracies in our measurements to be small enough so that it doesn't have that big of an effect on the total change in that surface area, specifically that 1% difference. So here's what we can say. As we're talking about the true change in our surface area, we want that to be within 1%. So we could be a little bit more or we could be a little bit less. What we're going to do is take the absolute value of this total change to account for either being a little bit over or a little bit under, but we want that to be within 1%, so we can say that we want that to be less than or equal to 1% of the S value. So I'm going to say 0.01 S, but that 0.01 we can really write as 1 over 100 times S, and then we know that the surface area formula is 4 times pi times r squared, so I can really write that as 4 pi r squared over 100. Now as far as that true change in the surface area, we can approximate that by using ds just like we did in the previous example, and to do that we took the derivative of our surface area formula and then multiplied by the change in the radius. So the derivative of our surface area formula was 8 pi r, and then the change in the radius is just dr. So I'm going to take that information and plug that in for this change in S. So this will say the absolute value of 8 pi r dr, we want that to be less than or equal to this 4 pi r squared over 100. Now we're going to go through and solve this for dr so that we can figure out what that percent difference would be. Now since this radius is always going to be measured as a positive length, we're allowed to safely divide that out of these absolute value. So that's going to leave us with just the absolute value of dr being less than or equal to, now what I'm going to do is take this 4 pi r squared over 100, but instead of dividing that by 8 pi r, I'm really going to think about it as multiplying by 1 over 8 pi r. And that's going to let us do some reducing in here. So because we have a pi on top and on bottom, we can cancel that out. I can cancel this r on bottom with one of those r's on top. This 4 and this 8 can be reduced down, so that 8 becomes a 2 and that 4 becomes a 1. So now if we look at multiplying the things across the top here, we've got an r and a 1 left over, so that's just r on top. And across the bottom we've got 200. Now I would really think about separating this out and writing it as 1 over 200 times r, but 1 over 200 is 0.005 r. Now if we look at this decimal 0.005, and if we were to convert that over into a percent, that would be 0.5 0.5%. So we want to measure the length of our radius with an error of dr so that the difference is no more than 0.5% of the true radius. So one more example we're going to take a look at here. So in the late 1830s, the French physiologist Jean Poisoy discovered the formula that we use today to predict how much the radius of a partially clogged artery has to be expanded in order to restore normal flow. So his formula was V equals KR to the fourth power, and that says that the volume V of fluid flowing through a small pipe or a tube in a unit of time at a fixed pressure is a constant times the fourth power of the tube's radius r. So we want to figure out how a 10% increase in that radius r will affect the volume V. So the first thing we want to look at is the absolute change. So the change in the volume can be approximated by finding the derivative of that volume formula times the change in the radius. So if we look at doing the derivative of that volume formula, we would drop the 4 down as a multiplier, so it would be 4kr cubed times the change in the radius. So that's the absolute change. Now if we wanted to find the relative change, we would want to divide this by the initial volume, which is just our V value. So we're dividing this by V, but we know that our volume formula is KR to the fourth. So on the right-hand side where we're dividing by V, I'm actually going to plug in that KR to the fourth there. And then if we look at reducing down that right-hand side, we can cancel out this K value. We can cancel out 3 of these R's on top with 3 of them on bottom, but there will be 1 left over. So we can say that the relative change in the volume is going to be 4 times the change in the radius, all divided by the radius. Now this dr over r really represents the relative change in the radius. So we can say that the relative change in the volume is 4 times the relative change in the radius. So if we know that there's a 10% change in the radius, then that's going to produce a 40% change in the flow. That's going to be it for this video. Thanks for watching.